Okay, so as promised, we are going to talk about synthesis, right? This is the big deal in organic chemistry. I would say it's probably the most elegant thing that we do, and I would say to a general audience, those who are not going to be professional chemists, synthesis is certainly the most valuable thing that I can bring to the student in chemistry, just in terms of sophisticated thinking and developing you as a thinker. So synthesis looks basically like this. I've told you before, I think, that you're going to be asked to make B from A, right? And we're typically going to write that like this. We're going to say B comes from A. That's how we're going to write it. These two are the same statements, okay? Now, what we don't mean is that there's one reaction that takes you from A to B. That's not what we mean. What we mean is A might go this way, it might go this way, over here, down there, and then back up to B, right? There's lots of ways to get to B sometimes. And in the simplest case scenario, it's just going to be one reaction. But oftentimes it's going to be more than one. So we have to get used to how to think like that. In the one case, if suppose we're supposed to develop some path from A to B, we might be thinking, all right, well, what does A could make that, it could make this, it could make that, it can make X, let's say Y and Z. And then you have to think, well, none of those are B. So oftentimes what I'll do is I'll go to B and I'll say, what can make B? What can make B? Let's see, I can make it from M, I can make it from N, and oh yeah, I can make it from X. Look at that. Okay, I see now. My pathway is going to be A to X to B, right? That's how I think with this, and I think that you're going to end up sort of going the same way. All right, so let's look at some synthesis strategies. To set up a synthesis, you first of all have to look at the reactants or the starting material and the target compound. In the target compound, I see I've got an X and a Y, right? Aha, okay, I did an addition reaction. That's an addition because I've got a double bond here and I have, the same number of carbons, but I got an X and a Y in there. Now, in another case, I've got X and Y like this, right? I say, oh, why? That's just a substitution, right? And then sometimes you see you've got something here, and then it goes, oh, wait a second, double bond, that's an elimination, right? So you'll have to train your eyes. Of course, if you have the reactions memorized, you're at a huge advantage. Well, actually, I don't think it's possible unless you have the reactions memorized. So, but once you get your eyes used to this, it becomes routine. And I would say it was definitely the most fun thing for me as a chemistry student. I wasn't expecting to become a chemistry professor, right? I wanted to go into healthcare, and somehow, once I got to synthesis, this just really captured my attention. It really can be a lot of fun. So let's look at an example. If you're asked to take something like this, okay, and make this from it, you say, wait a second, I've got a double bond here, and aha, okay, it looks like I'm going to be adding an OH here and a hydrogen here. So it looks like I'm adding water across a double bond. It also looks like this functional group went to the most substituted carbon, so it's going to be Markovnikov, right? And so I have to search through my memory banks and say, what gives me a Markovnikov addition? I know that I've got two reactions that give me a Markovnikov addition. Acid and water, right? Which we oftentimes will do maybe H2SO4 and water, same thing. These two reactions are the same thing. And we also have mercury, HgSO4 and acid, right? And water, okay? So, in sulfuric acid, H2SO4 and water, right? Okay, those two reactions are these. This is a reaction and this is a reaction. This one appears the same as both of those. All right. So it turns out that we're going to, for this case, there's no rearrangements possible. So this is going to be good enough. All right. So let's think about another example. What if we change the leaving group, change the position of the leaving group, right? That's confusing. It could be terrifying because you say to yourself, well, I don't have a reaction just clips this off and brings it over. That's what looks like it's going on, but that's not what's going on because you also have a hydrogen here, right? So really what's going on is these guys are switching places. Well, how is that possible? Well, it's going to take two reactions, right? So the first reaction is going to be an elimination where you make a double bond. And so you can see that this bromine, you can see the bromine's going to the more substituted position, right? So if I do an elimination, and then all I'll have to do is just a Markovnikov addition, right? You see that? Okay, so the elimination, you need a Zait. I should have said that in the previous slide, right? You need a Zaitsev elimination because you have to bring the double bond to that side. So the way to do that is with a non-bulky base, right? This is a small base. This is a big base. The big base takes it to the Hoffman elimination, takes it to the outside. All right. So after we do that, then we simply do a Markovnikov addition. Okay, now let's look at another example. So suppose you were asked to do this transformation. You would say to yourself, wait a second, looks like I'm just clipping this off and putting it back on this other carbon, right? So it's going to take an elimination. And this time the elimination is going to have to go, it looks like that's a Hoffman elimination, right? Because the Markovnikov elimination would be over here. I'm sorry, the Zaitsev. Am I saying that right? No, it's eliminations are, sorry, Zaitsev and Hoffman are additions. Sorry, it's a Zaitsev, it's a Markovnikov is the addition. I beg your pardon. This is the Hoffman elimination, not the Zaitsev elimination, right? Zaitsev would be here. I think I did say that right the first time. And then we have to add an anti-Markovnikov, right? Because this would be if you add an H2O across here, that's the more substituted position. That would be the Markovnikov addition, right? So we have to do anti-Markovnikov, and that would be over here. So we do the Hoffman elimination, Hoffman, and then we do the anti-Markovnikov. Remember how to do the anti-Markovnikov addition? Okay, so first of all, we have to make a good leaving group, right, to do the elimination. Forgot about that, right? So a good leaving group, we gotta make this a tosylate first of all. So now I've got a really good leaving group. Hydroxide's a horrible leaving group, right? So I make it a good leaving group, and then I eliminate with Hoffman, and then I add here. And my Hoffman elimination is going to be a big bulky base, right? And then don't forget this is 2 steps. It's BH3 complex with THF, and it's hydrogen peroxide and base. Okay, that's cool. Very cool. Very powerful. All right, what about if I'm changing the position of a pi bond? Right, so here I've got the more substituted double bond, and over here I've got the less. Okay, so this is clearly going to be a Hoffman. I'm going to be doing a Hoffman elimination. Can you see what I'm doing here? I'm first of all adding a functional group, and I've got to add the functional group anti, right? And so it's going to come here, because if I do it a Markovnikov addition, the bromine's going to go here, right? But the anti-Markovnikov, it's going to go over there. Okay, so how you do an anti-Markovnikov addition of HBr? Right, remember we did that with peroxide. Okay, there was a couple peroxides we used, but peroxide and HBr. Okay, and that'll give us the anti-Markovnikov addition. And then the big bulky base is going to give us the Hoffman product. All right, so in review, we've learned 10 reactions with this chapter. This is an elimination. I'm sorry, this is an addition. Man, I'm just really not saying things clearly, am I? Okay, that's an addition. This is 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 an addition. And this is not. Let me change colors for that. Ozonolysis is not an addition. Starts out kind of like an addition, but then it just cuts. Okay? So cool reactions. I hope you have 10 3x5 cards for these reactions. You're going to need them. Super powerful. And then here's a graphic to sort of give you some view, a big picture view of all of that, right? Ozonolysis is where we cut it, right? We take this that's the last one I showed you. Cut that double bond, and if you cut it and put oxygens there, you're going to end up making opening up the ring. That's going to be very scary until you're used to it, right? Okay, so these are the 10 reactions. I won't walk through all of them with you. Make sure you've got 3x5 cards. These are actually more than 10 reactions. There's more than one way to add water across there, and so on. So go make sure you have all these reactions on 3x5 cards and practice them. See what you can do with them. Good luck.